Hey everyone, today's topic is geometric sequences in series. It's going to feel a lot like what we did yesterday, looking at the arithmetic sequences in series, where it's a similar concept. Your sequence of numbers is just a list of numbers, and then your series is going to be the sum of that list. With the geometric sequences in series, we just have a different pattern. So for arithmetic, we said the pattern was that we would add or subtract a fixed number to get from one term to the next. If it's a geometric sequence or series, then you're going to be multiplying by, or dividing, which is the same as multiplying by a reciprocal, but multiplying by a fixed number to get from one term to the next. So a geometric sequence is a list of numbers, and it's formed by multiplying by a fixed number. And the fixed number that we multiply by we call the common ratio this time. So what's the ratio from one term to the next? And we use the letter R for that, or to denote that ratio. And the common ratio is sometimes going to be something that's easy to see. For example, in our first list here, it's pretty easy to see that to go from 3 to 2 or 3 to 6 or 6 to 12 or 12 to 24, that we're just multiplying by 2. So we would say that the common ratio in this first list is 2. And we call it a common ratio because if we made a ratio of any of our two consecutive terms, so second term to first term, for example, 6 over 3, we get 2. Or 12 over 6, we get 2. Or 24 over 12, we get 2. Okay, so if we take a ratio of two consecutive terms, we're going to get a ratio of 2, so the common ratio is 2. But again, that just means we're multiplying by 2 to get from one number to the next. Now, if our number is getting smaller, that means we're going to be multiplying by a fraction, or we're dividing, right? To get from 256 to 64, if you can't see what you're multiplying by or dividing by to get from here to here, then we work in reverse. So instead of what do we multiply to go from 256, so 256 times what number makes 64? Well, let's just divide the 256 over, right? If we divide 256 over, we're going to figure out what that number has to be. So I can always figure out my common ratio by working backwards. If we take the second term and divide it by the first, so if we divide our second term by our first term, we can see R. So in this case, R is going to be 64 divided by 256, and that's going to reduce to 1/4. Now that's a little easier to see here. I can see that I'm dividing by 4. So if I'm dividing by 4, the ratio that I'm multiplying by is 1/4. Okay? Now, I think that one you probably still could see maybe a little easier than this one. So this is where it's really helpful to use division, working backwards. If we take the second term, 0.294, divide by the first term, which is 0.42, then we can see what our common ratio is. And let's use the calculator on that. So 0.294 divided by 0.42 says our common ratio should be 0.7. So 0.7. That means if we multiply 0.42, right, 0.42 times 0.7, we should get to 0.294. And if I multiply by 0.7 again, then it takes me to the next number, 0.2058, and that's how the list would continue. Okay? So a geometric sequence, we're multiplying by the same number to get from one term to the next, or dividing, which is multiplying by some fraction or decimal. And we have the same types of things that we looked at yesterday that we should be able to do with these sequences. So one would be writing or using an explicit formula. Remember, the explicit formula is used to find or calculate any term that's on the list. So the lists above, if I said to, find the 5th or 6th term, we don't need a formula for that. But if I'm asking you to find a term that's farther out, or even on the third one, if I wanted to know, let's say the 6th, I don't know if I want to carry those decimals out that far to find all 6 of those terms. So the shortcut to finding a term on the list is to use a formula. Now this formula is going to look a little different. So it says that any term on this list can be found by taking the first term and multiplying by the common ratio and raising that to the n-1 power, where n represents the term number. We saw a sub 1 yesterday as the first term, and then r we just defined as our common ratio. So let's write an explicit formula. If our sequence starts at -6 and our common ratio is 3, then any number on this list, a sub n, is going to be that first term, -6, multiplied by the common ratio of 3, and then raised to the n-1 power. So that's how the explicit formula would look for that sequence. And then if we wanted to find a number on the list, then we're going to be plugging n in to figure out that number. So now if we want to find the 15th term, we know n equals 15. So a sub 15 this time. Okay, we start this list at a sub 1, 8. We're multiplying by a common ratio of 4. And then instead of raising it to the n minus 1 power, it's going to be raised to the 15 minus 1 power. And that's just a calculator problem from there. So I'm going to use Desmos. So 8 and then 4. And then we want to raise that to the... Now if you're doing this in a normal calculator, make sure that the 15 minus 1 or just 14, if you don't want to make a mistake, ends up in the exponent. I see people in a calculator a lot do 15 like this, and then the minus 1 not being in the exponent is going to give you the incorrect answer. So make sure the minus 1 is with the 15 in the exponent, or just take the 1 from the 15 and make an exponent of 14 here, right? But if you're going to type in the 15 minus 1 because you don't trust yourself, it can't look like that. The minus 1 would have to stay, oops, now it's not going to let me do it. Let me go back here. Minus, nope, 15, let me put a 1 in there. Make sure the 15 and the minus 1 stays in the exponent. Okay, so we have this 2.147 blah, blah, blah times 10 to the 9th. If your calculator does this, or if Desmos does this, this is scientific notation. So 2.4, oops, I can't transfer. 2.147483 and then 648 times 10 to the 9th power is scientific notation. It would be okay to leave your answer like that, but if we multiplied this decimal times 10 to the 9th power, what's going to happen is a decimal is going to move 9 times. So this is scientific notation. Okay to leave your answer like this, but the preferred answer would be a normal number, a normal standard notation. So this 10 to the 9th power means to move the decimal, move your decimal 9 times to the right. And if you saw that kind of notation, the scientific notation, and the exponent was negative, then you would move your decimal to the left. So this is really the same thing as 2, and then if we moved it 9 times, 1, 2, 3, 4, 5, 6, 7, 8, 9, the decimal would be right after the 8. Get rid of all those dots. So this is equivalent to 2, 1, 4, 7, 4, 8, 3, 6, 4, 8. Put some commas in so I can read it. So that would be 2,147,483,648, right? If I was looking for the 15th number on that list, having to start at 8 and multiply by 4 15 times to get to that number would be kind of ridiculous. So using the formula to shortcut is definitely more efficient. Okay? All right, here's one for you to try. If you want to pause your video, give it a shot. Otherwise, continue to work here along with me. So 12th term, we're looking for 12th term, n equals 12. So the 12th term, a sub 12, is going to equal the first term, negative 4,096, multiplied by the common ratio, 0.25, and that's going to be raised to the 12 minus 1, or the 11th power. Now, before we put anything into the calculator, we should have an idea of what's happening. Like on the last one, we ended up with a huge number, which makes sense because we were multiplying by 4. Well, if we're multiplying by 0.25, that's like a fourth. We're dividing this number by 4 as we move along. We're going to end up with a not as big of an answer as we had in the last one, right? The numbers that we're adding together are going to be getting smaller, all right? So just so you have an idea of what you're doing before you go to your calculator. So let's put in negative 4,096, parentheses, 0.25, close it, and we're going to raise it to the 11th power. So we end up with that decimal, or if I wanted to make that a fraction, I don't know that that looks any better. Either one of them would be fine. I'm going to go ahead and put the fraction. So we're looking at a negative 4,093 over 4,194,304. Or the decimal, totally fine too. It's a negative point. Oops, I typed that in wrong. Jeez, guys. If we were in class, one of you would have yelled at me. You see what I did in Desmos? I got a 3 there instead of a 6. Let me fix that. Okay, so that decimal, or, oh, that fraction looks much better. Negative 1 over 1024. And again, if you wanted to leave the decimal, that's fine. I think the fraction's easier to write, but whatever works for you. So the 12th number on this list is negative 1 over 1024. Okay? All right, so the explicit formula, just like we saw yesterday, is for finding a term that's on the list. The recursive rule is another formula, but it doesn't really do anything for us. Remember, this is a way to mathematically state the pattern. It shows the pattern that's happening here. And so to write the recursive rule, we need to know what our common ratio is, because that's what's going to vary from one number to the next. So we want to state our first term, and then we're going to say that any number on this list is r times the previous number. So we established yesterday the previous number is a sub n minus 1. If we take any previous number, multiply by r, we're going to get to the next number. Or you could say that if we took any number on the list and multiplied it by r, let me scooch this over. If we took any number on the list, a sub n, and multiplied it by r, we would get to the next number. And the next number we would say is a sub n plus 1. So either one of these are fine. I just prefer the one that's in blue. But as long as you state the first term, either one of those is mathematically fine, appropriate. Okay, so if we look at the example, this geometric sequence starts at -5. So we're going to say a sub 1 is -5. And the pattern here is, what are we doing to multiply, or what are we multiplying by to get from -5 to 15 is a -3. So if we're multiplying by -3, let's say r equals -3. So we would say that any number on this list is -3 times the previous number. And that would be our recursive rule. Or again, if you wanted to say that if you took any number on the list and multiplied it by -3, then we would get to the next number, a sub n plus 1, that would be fine as well. Okay, so either one of those. Again, I just prefer the other option, but both are fine. All right, so we have the explicit formula we can use to find terms. We can mathematically state the pattern using what we call the recursive formula, recursive rule. And then a series, just like yesterday, would be the sum of all of the terms in our sequence. So a geometric series is the sum of our geometric sequence, and we're actually going to be able to evaluate or find the value of the sum of both finite and infinite geometric series, and I'll show you the infinite, which sounds crazy, right? I'll show you the infinite in a minute, but for now, if it's finite, that means we have a set list of numbers that stops. If we're going to evaluate the sum means to add the terms, right? Add up all the terms, figure out what that sum is equal to. And sometimes, so there's a formula just like there was for arithmetic. The formula, though, it gets a little bit more tricky than the arithmetic. So if you don't need a formula, like if you're just asked to add, let's say, 4 terms, I wouldn't use a formula to add the 4 terms. Just put the 4 terms in the calculator and add them. So sometimes a formula is not going to be necessary. But if our terms are ugly, or if we're adding up a whole bunch of them, maybe we don't want to add them all by hand. So if it's a more complicated or a lengthy sum, or if you just have no issues with the formula, then your formula says the sum of n terms is going to be equal to the first term multiplied by 1 minus the common ratio to the nth power, and then divided by 1 minus the common ratio again. And again, this could be a little trickier to use even if you're using your calculator. So if you wanted to avoid using the formula, I totally understand. So for example, in this next problem here, we're finding the sum of the first 4 terms. I probably wouldn't use a formula for that. So this list is going to start at 9. And then if we're multiplying by 3, the next number would be 27. The next number would be 81. The next number would be 243. And if I wanted to, I could continue the list. But here we're looking for the sum for these first 4 terms. So if I add the 9, the 27, the 81, and the 243, what do we get? Calculator says 9 plus 27 plus 81 plus 243 is 360. So the sum for these 4 terms, 360. Okay, no formula needed to add up 4 numbers. The next one is definitely looks a little different. If you want to try it out, give it a shot. Otherwise, if I want to add up all the terms in this list, I have to know what all the terms are. So our list starts at 1, and then it goes to 5, which means we're multiplying by 5. So 5 times 5 means one of the numbers hiding from the middle is 25. 25 times 5 is 125. And then 125 times 5 is going to get us to the 625. So the missing numbers were 25 and 125. Now I just got to add all those together. So the sum for these 1, 2, 3, 4, 5, 6 terms, 1 plus 5 plus 25 plus 125 plus 625 is going to equal, well, let's see. So 1 plus 5 plus 25 plus 125 plus 625 is 781. Okay, no formula needed to add, 4 or 5, a handful of terms. And these terms don't have any decimals or fractions, pretty easy to type in. Now, if I was looking for the sum of 12 terms, I don't know that I want to list out those 12 terms and then put them into a calculator and add them all up. Could I do it? Absolutely. It's just not something I would choose to do when I know I have a formula. So the formula says the sum we're looking for 12 terms, sum of 12 terms is going to equal the first term, which is -4, multiplied by 1 minus, the common ratio is 2.5, and that's going to be raised to the nth power, and n was 12 terms, and then we're going to divide that by 1 minus the common ratio, and notice I plugged in the common ratio with parentheses. Not so important when it's a positive common ratio, but definitely important when it's negative. But rather than having to differentiate when to do it and when not, it's always a good idea to use parentheses when you plug things in. Okay, so this is just going to go into the calculator now. Let's see, get rid of some of this. I'm going to hit my divide to make a fraction first. On the top, I've got a -4, parentheses, 1 minus another parenthesis, 2.5, close that, raise it to the 12th power, and then close the big parentheses. There's the top. On the bottom, 1 minus 2.5, and there it is. Gigantic sum, which should make sense. We're starting at -4, multiplying by 2.5, so the number is going to keep growing. So we're looking at, if I can squeeze this all in here, 158,943. Oh, that's a decimal? Let's see. Oh yeah, decimal, because we're multiplying by decimal. Let me see if the fraction's any better. Here, I don't know if the fraction or a decimal, they look equally annoying to write, so I'm going to just pick one. All right, let's go with the fraction. So -813,788, -813,788, I think it was 43 over 512. Okay, either that or the decimal will be perfectly fine. I just chose the fraction, but if you want the decimal, -158,943, -158,943.052,734. 052,734. Okay, so either one of those is fine. I mean, you could see how it would be pretty annoying to have to make that list of 12 numbers and then add them together to get one of those as the result. All right, so there's one for you to try with the formula, with the calculator. Again, pause it if you want to give it a shot. Otherwise, we are looking for the sum of 10 terms. We have a list that starts at 2, and then we multiply by -3. So it's 1 minus a -3 to the 10th power, and then on the bottom 1 minus a -3 again. And so calculator says, all right, we hit the divide button. On the top 2 parentheses, 1 minus parenthesis again, -3 raised to the 10th power, close the parenthesis. On the bottom, 1 minus parenthesis -3, and on the bottom, if you wanted to make that just a 4, like, I get it, it's fine. So -29,524. -29,524 is the sum for those 10 terms. right? And if that's not what you're coming up with in your calculator, be really careful about putting those parentheses in, and make sure when you close your parentheses, oh, it won't, right? But in the top here of the fraction, if you're in your calculator and you do -3 and you close the parenthesis and then the 10 and you close it here instead of closing it here, it's going to affect your answer. So be really careful about how you're typing that into the calculator. Okay? Good news is, if you prefer Desmos to do the work for you rather than just using the formula, Desmos uses the sigma notation. So we can also evaluate by hand or using Desmos with our sigma notation. So here, if we wanted to do this by hand, we would be looking for the sum of, from 1 to 6 would be 6 terms. You would take a little more thought here. So the first number on the list would be found by plugging a 1 in. If I put a 1 here, 1/2 to the first power would be a half. So this list would start at a half. And then we have 1 minus the common ratio. The common ratio is oh, I think I screwed that up. Sorry, my brain. Think about your explicit formula that we had up here. Where did we go? Over here. The number outside of the parentheses is our first number, and the number inside of the parentheses is our common ratio. So going back here, we have technically a 1 out here. So our first term would be 1, and then our common ratio would be a half, and then we raise it to the 6th power, and then we'd have 1 minus the half on the bottom again. Or, and if you put that into Desmos, it would spit out the answer. Or, since we're going to have to go to Desmos either way, right, we just plug in this sigma notation right to Desmos. So I'm going to go here and go to functions, miscellaneous, there's my sigma. We're going from 1 to, on the top, 6, and then we're going to put in a parenthesis 1/2, close, see, don't close there, close there, and then we're going to raise that to the nth power. And then it's going to say that the sum of those 6 terms is 0.984375, or as a fraction, I always like to see if it's easier to write, is 63/64. So I'm going to go straight to my answer of 63/64 using Desmos. Okay, so again, feel free to pause and try this one out. We're looking at functions, sum from 1 to 10, so it's 10 terms. This list would start at 2, and we'd be multiplying by 3 to continue the list, which means we're going to end up with a much larger answer here. And the nth power tells us we have 177,144 for our sum. 177,000, I forgot, 144 for our sum. I guess technically we should say the sum for these 10 terms is 177,144. And then here we should say the sum for these 6 terms is 63/64. And again, if you wanted the decimal there in place of that fraction, that would be fine. Okay? So these are sums for finite series. That means a countable list of numbers, a list of numbers that stops. Now we can actually evaluate the sum of an infinite series as well, a series that goes on forever. But we won't be able to do this all of the time, and this should make sense. Let me take you to my scratch paper for a second. So if I had a list that, let's say it started at 1, and I was multiplying by, I don't know, 5. So 5, and then times 5 would be 25, and then times 5 would be 125. What's going to happen if I keep multiplying by 5 is this number is going to get really large really fast, right? So if I go to add these numbers up, the sum here, if I wanted the sum for the 4 terms, right, the number is going to be pretty large. And then if I add the sum of 5 terms, it's going to be larger. And then 6 terms is just going to keep getting larger and larger and larger, right? So I won't be able to find a list, the sum of a list that goes on forever if the numbers continue to get larger and larger and larger. But if I was going in reverse, okay, let's say I started at 125 and I was dividing it down by 5. So divided by 5, or multiplying by a fifth, right, would take me to 25, and then divided by 5 would be 5, divided by 5 would be 1, and then I have a fifth here, and then I'd have a 25th here, and then 25th here, And once I continue to add here, the fraction is going to get smaller and smaller and smaller. So if the fraction gets smaller and smaller and smaller, it has less and less of an impact on the sum. So what's going to happen is the sum of this type of series, even though it's going to continue on forever, the fractions that we add way out here aren't going to impact the overall result. So we would say that this sum is going to converge to some specific number, and we can calculate what that specific number is. Okay? So if it's a infinite series, if the series is if it is divergent, remember what I wanted the blank here. If the series is divergent because your common ratio, your r, and its absolute value of r, doesn't matter if it's positive or negative, but if we're dividing, which means we're multiplying by some fraction or decimal that's less than 1. So if our common ratio, the absolute value, is less than 1, so like we have something like multiplying by a third or 3/4 or something that's going to be making the number smaller every time, then we're, oh, this is not right, backwards. I'm sorry. If it's divergent, then the number that we're multiplying by is a number that's bigger than 1. Bigger than 1. That means the numbers are going to get bigger and bigger and bigger. Then we won't be able to evaluate that sum. The sum cannot be evaluated. Now, if it's the other way, if the absolute value of our common ratio is something that is less than 1, so this is where we're dividing our number down, or multiplying by some fractional amount, then the fractional amount that we add doesn't affect the sum as we go farther and farther down the list. So that's what we call a convergent series. And if we have one of those, then we have a formula. It says the sum, and there's no subscript here because there isn't a number of terms. So we're just going to say the sum is going to be equal to the first term divided by 1 minus the common ratio. Okay, so looking at the first example, since the common ratio here is 3, multiplying by 3 to get from one number to the next, the numbers that continue here are going to get bigger and bigger and bigger. It means when we add find our sum every time, it gets bigger and bigger and bigger. So we would say that this is a divergent series, so it's not possible to find the sum. Oops. Desmos popped in there, sorry. Okay, now if we look at the next one, 10 to 2, 2 to 2/5, 2/5 to 2 25ths, we are dividing by 5. That means our common ratio is 1/5. So the fraction, as we move down this list, gets smaller and smaller and smaller. That means that this is convergent, that this sum is going to converge to some number. So the sum for these terms, no matter how far we take this list out, right, forever, is going to be equal to that first term of 10 divided by 1 minus the common ratio of a fifth. So 10 divided by 1 minus 1/5. And that tells us that the sum is going to be approaching 12.5. So if I just kept adding these, like if you just add the 10 and the 2, you're at 12, right? And then we add a fraction, add a fraction, add a fraction. The smaller and smaller fractions, it makes sense that we're getting close to 12.5 as a sum. So 12.5 would be our sum. Okay? Now here we have another one. Again, if you want to try it out, feel free to pause. What are we multiplying by to go from 1 to 2/3? Well, we'd have to be multiplying by 2/3 to get from 1 to 2/3. And 2/3 is less than 1, which means the value of this fraction is going to get smaller and smaller and smaller, which means, again, we have a convergent series. So our sum for this convergent series is going to be the first term divided by 1 minus that common ratio. So would that be a third? It's going to be 3. Just don't trust my math here. So the first term divided by 1 minus the common ratio of, 2/3. And yeah, 3. So the sum is going to be approaching 3. Okay. And I got one application here where using a geometric sequence or series might be useful. So it says, for her New Year's resolution, Brenda decided to start a savings account, and she plans to deposit a whole penny in January, 3 cents in February, 9 cents in March, and so on. Seems like a pretty risky plan, right? So the first number on the list is 0.1. The next number on the list is 0.01, 0.03, then 0.09, and this will continue. Where this was January, February, March. How much money is she going to deposit in December? So December would be the 12th month of the year. We're just looking here for what is that 12th deposit going to look like. So this question is asking for a sub 12. Well, a sub 12, that's a term on the list. We can use our explicit formula for that. A sub 12 is going to equal, we said the first number on the list is 0.01. What's the common ratio? If we go from 1 penny to 3 pennies to 9 pennies, well, we're tripling. We're multiplying by 3 to get from one number to the next. And we're going to raise this to the 12 minus 1, or 11th power. What do you think? She's going to have a pretty big deposit or a ridiculously small deposit? I think you're going to be surprised here. So starting at a penny, tripling the amount we deposit, and then 12 minus 1, so the 11th power. So in the 12th deposit, right, she ends up depositing $1,771.47. I don't know about you, but that's a surprising amount. So when you're tripling, your numbers are going to start to grow really, really fast. Okay, $1,771.47. $1,771.47 gets deposited in December. So that's just her December deposit. If we want to find the total amount she's deposited over the year, that means we want the sum of all of those deposits. So we're looking for the sum for the 12 deposits. Now that's not a infinite, right, amount of deposits, it's finite. So our sum formula for a finite series says to start with the first term multiplied by 1 minus the common ratio of 3 to the nth, in this case 12th power, and then divide by the 1 minus the common ratio again. And I forgot some parentheses. All right, so we're going to put this in the calculator, and I know that she's going to have, you know, more than $1,700 in there because that's how much she deposited in December. So let's see how this ends up. Over the course of the year, even though she started with a really small amount, how much is she going to end up with? So 0.1, 1 minus 3, oops, close that, 3 raised to the 12th power, and then 1 minus 3 there as well, and $2,657.20. $657.20, and that is the total amount for the year. So you may have been laughing inside, right, saying, okay, some New Year's resolution, putting a penny in January, right? Seems a little ridiculous, and it definitely starts out small, but because you're tripling, the amount starts to grow so fast that she ends up with over $2,600 in the account. So I don't know if this is reasonable. First half of the year, making her deposits would be pretty simple, but I don't know about you, just an extra $1,700 having to go in December. I'm not going to have that myself, right? Especially in December when you're shopping for Christmas and stuff. But anyway, you can see now the concept of the amounts growing really quickly like this ties into exponential functions. And when we get to that unit a little later on, we'll make some connections back to this. But for now, that is it for our additional topics unit. If you have questions, as always, email me. Beginning on Monday, I put an announcement in. Hopefully you saw it. Beginning on Monday, we're starting our quadratic unit.